Hi, welcome to the third and last part of Lecture 7 about continuous wave modulation. In this lecture, we'll be talking about transmission bandwidth of a general FM wave given a message signal or the properties of a message signal. In the previous lecture, we talked about single tone modulation. Now let's generalize it to a M of t that with known properties. Okay, and we'll also talk about how we detect FM. Right. So the FM spectrum for a narrowband approximation is the same as that of a full AM wave. Okay? But for a wideband FM, your spectrum may look like this down below as you see here. Okay? Majority of an FM wave spectral components are contained within some plus minus delta F. See example 4.2 of the book of Hykin for that. Okay? However, the true FM wave has a bandwidth that expands infinitely from the center frequency. Okay? Since the Bessel functions extend from negative infinity to positive infinity. Okay? So one way of approximating the transmission bandwidth of FM is if a FM wave is effectively limited to a finite number of significant side frequencies compatible with some specified amount of distortion. So if you move away from FC, the side lobes or the delta functions gradually decrease until it becomes very insignificant, very insignificant. So if we remove those insignificant side lobes, maybe just get this part of the spectrum, we transmit that part of the spectrum, we can transmit an FM wave with minimal distortion. Effectively, we have a bandwidth that we can use to transmit an FM wave. We can approximate that bandwidth. And we use the Carson's rule for that. So the bandwidth of an FM wave is approximately equal to twice the sum of the message frequency plus the maximum frequency deviation. And since there's a relationship between the maximum frequency deviation and your message bandwidth, we can rewrite Carson's rule as Carson's rule as this. Okay? So some observations for large beta or wideband FM, the bandwidth approaches and is slightly greater than 2 delta F. So beta is very if beta is very large, then 1 over beta is approximately 0. Approximates something slightly larger than 2 delta F. For small beta, then the spectrum is effectively limited by the carrier and its two immediate side frequencies, and this is what we've shown before, that for small beta it looks like your FM wave is just a full AM wave, and thus uh, your bandwidth is approximately 2 times the message frequency. So a better approximation of BT. So Carson's rule is widely used due to its simplicity. So maybe there's an alternative. The transmission bandwidth of an FM wave is the separation of between the two frequencies beyond which none of the side frequencies is greater than 1% of the carrier amplitude obtained when the modulation is removed. Okay? So we will find an N, okay, an N max, that has the largest value that satisfies this requirement. Okay? That's it. And if you find that N max, you multiply 2 to that times FM, you'll get the transmission bandwidth, effective transmission of bandwidth of FM. Any side frequency that has a magnitude less than 1% of the carrier, or 1% of the carrier amplitude, is already insignificant. If we remove them, the distortion will be minimal. So this is a better approximation for the transmission bandwidth. Okay? Now, let's look at the bandwidth for an arbitrary M of t. For some arbitrary M of t, let's say the bandwidth of W, we can extend the Carson's rule to determine the worst case evaluation of the transmission bandwidth. So why do we use the worst case evaluation? If we're talking to a client, let's say, and the client asks us, why is the bandwidth this large? Okay. This is the worst case scenario that the bandwidth will occupy. Okay? It could be less than that, but this is the worst case scenario, and let's prepare for the worst. When you're trying to create an engineering, or if you have an engineering design, you always think of the worst case scenario for your design. So if you're looking at the FM bandwidth, we use the worst case scenario, or the worst case evaluation of our transmitted signal. So at the very least, if we are sure that the FM signal uh, go will not go beyond the worst case evaluation, right? And if you calculate the worst evaluation incorrectly, there will be repercussions, especially when we're talking about transmitting over a limited spectrum, where if you go beyond your assigned bandwidth, you will interfere with different users. Okay? So, for a general message signal with a bandwidth W, we introduce the parameter, the deviation ratio, defined as this. It's the ratio of the between the frequency deviation and the highest frequency component of the message. And then we just replace beta with B and FM with W. That's it. And we have the worst case evaluation for the bandwidth of FM using Carson's rule. It's equal to this equation. Okay? So if we analyze that for PM signals, as we have said before, since PM signals are related to FM waves, thus the formulas, we just need to slightly modify them to be applicable for PM. So the frequency modulation has a modulation index delta F over F sub M. Okay? Instead of, if we relate that, if we go back to the expression for an FM wave, so you have cosine 2 pi FCT plus beta times sine 2 pi FMT. Okay? We'll just use the amplitude of your single tone signal. That is already your phase modulation. Now, if we use the cosine 2 pi FMT as the message signal for a phase modulated wave, then it's equal to cosine 2 pi FCT plus Kp A sub M cosine 2 pi FMT. And the amplitude here would now correspond to the beta of your phase modulation. Now, generally, we have, if we have a delta phi maximum phase deviation, okay, that will be your deviation ratio right here when we want to analyze PM waves. Okay, and the bandwidth, well, we'll just use the same equation using Carson's rule. So it's equal to this, it's still the same, but instead we have a delta phi. Okay? We use delta phi instead of delta F. And delta phi is related to W using this equation right here. Okay? And now this is the transmission bandwidth for your phase modulated wave. Okay. So now how do we produce FM signals? To produce FM signals, we can use a voltage-controlled oscillator to make the oscillation frequency dependent on the input voltage. And that's actually just simple. You have a V input here. We use a variable capacitor, a varicap, whose capacitance, well, capacitance varies with respect to the voltage input. Okay? If you change the capacitance, since the operating frequency of an oscillator is approximately 1 over square root of LC. If you change the capacitance with respect to the voltage, then you change the frequency with respect to the voltage. Right? Now you just need to have a process to linearize the fluctuation of frequency, and this is the direct FM method. Okay? So this is the equations for that. Your capacitance can be expressed as some central capacitance, DC capacitance, minus some sensitivity times m of t. And we can now get the instantaneous angular frequency from there. Okay, so we get the derivative of that with respect to time. It's approximately if you like this, right? And then we get this expression for your instantaneous angular frequency. Thus, the FM wave can now be expressed as this expression right here, and you have your frequency sensitivity right here. Okay. As you can see, the frequency sensitivity is dependent on the center frequency of your oscillator and the parameters of your varicap. Okay. An indirect FM method, since PM is less common than FM, but it can be used to generate an FM wave. So if we have a narrow band phase modulator or an Armstrong modulator, the PM wave is approximately in this has this expression. So there's a what do you call this? There's a limitation in the indirect FM method that your message should be in a narrow band to minimize distortion. And with that, we can now we use this PM signal right here and put it in an integrator, put the message in an integrator and put it in a phase modulator. You have your FM signal. Okay? So from here, we produce a PM signal. If we put the derivative of m of t in this phase modulator, we create an FM signal. Okay? And as this is, as you recall, that your FM and PM are related to each other. Okay? If we want to have a wideband FM, we add a frequency multiplier block for that. Okay? The frequency multiplier consists of a nonlinear device and, for example, a diode or a MOSFET or a BJT. And this will expand the spectrum of your output narrowband FM wave into a wideband FM wave. And we use a bandpass filter centered at the desired frequency spectrum so that we limit the transmission bandwidth. And now you get your wideband wideband FM signal. Okay. So the drawback of this is that you need more components to produce the signal. Okay. But it's easier to design this than designing an oscillator circuit. An oscillator circuit is actually difficult to implement. Okay. So now, how do we detect your FM signals? One method is to use a frequency discriminator. So recall that your FM has the following expression here. If we take the derivative of the FM signal, we can place the message at the envelope. So take the derivative of this, then you get this signal right here. Okay. So, however, how do you implement a differentiator? As you can see here, the signal will now have some amplitude envelope. So how do we implement a differentiator? We use a high-pass filter. Okay? So we use a high-pass filter for that, and you place the FM signal at the transition bandwidth of your high-pass filter. With that, you have a linear slope at that point, and you just need to have a linear slope in the transmission bandwidth of your FM, and you won't care about the response in the other side of that transmission bandwidth. Okay? So if you have a linear slope at some point of your filter, you place your FM signal there, okay, and you'll have a linear variation in amplitude. And with the linear variation in amplitude, you use an envelope detector and you recover your message signal. Okay? So now, just note here that your AM signal after the sloping circuit will have a modulation index, an AM modulation index. You need to make sure that the modulation, your AM wave after the FM wave is or satisfies the condition for it to be for an envelope detector to be used. Okay, and that's how you detect your FM signal. It's one method. But the problem here is that there is a DC bias because of using this envelope detector system here. We can remove the DC bias by using a DC block, or we can use a positive sloping circuit and a negative sloping circuit, both with their envelope detectors, and we add them, or subtract, you add this one, you subtract this one, you get your original message without the DC block. Okay? Another way to detect FM is to use the zero crossing. Recall that the zero crossings of an FM wave contains information about the message signal. So the block diagram looks like this. You have a hard limiter, which will limit the FM signal that will go in the comparator so that it won't break. Okay, and you put some error here as a parameter for the comparator. With that, you create pulses in the comparator, and the pulses will vary depending on the FM signal's zero crossings. Okay, and you integrate those pulses and add a DC block, you can recover your message signal. Okay, so for example, this is your FM wave. The pulse generator will be something like this. And if you integrate that and add a DC block, you'll be able to recover your message signal. Right, so this is how it works. The pulse generator produces a pulse with some width delta t and an amplitude a whenever your signal crosses v is equal to 0. Okay, so the number of pulses within a short period of time t is proportional to the instantaneous frequency. So the number of pulses is proportional to your carrier frequency plus your kfm of t. And this is an example of the generated output. Right? If we integrate that, since integration is just getting the area under the curve, the integrator output can be expressed as amplitude of the pulses, width of the pulses, times the number of pulses. So that's the area over one period. And the number of pulses is dependent on the frequency content and dependent on the instantaneous frequency rather of your FM wave. Now you integrate that with respect to time, you get this equation right here. Your m of t is there, but you have a DC component that can be removed using a DC block. Okay? And that's the end of this lecture. So there are a number of ways to detect FM. So if you need any clarification with any of them, do not hesitate to leave a comment in the comment section below. Thank you for listening. This is the end of Lecture 7. See you next meeting.